Okay, so let's look at second and higher derivatives. What we have been discussing so far is the first derivative, because we only differentiate once. So all this dy by dx nonsense we've been mentioning all along is the first derivative of the function. Okay, we can always discuss higher derivatives because they are useful in some situations. For example, with your second derivative, you can solve optimization problem. We're going to look at that in a while. You can solve problem on motion as well, kinematics. Like if you differentiate speed with respect to time once, you get your distance with respect to time once, you get your speed. The second derivative gives you the acceleration or deceleration, as the case may be. Okay, you can use optimization problem to know. You did in quadratic. If you write something in different and completing the square, you can get the turning point, right? But some functions will be so funny that you don't have to write all those quadratic stuff or plotting the graph. Calculus can always help you to know where the turning point is. That is what you're going to learn in second derivative, how to apply it. So, second derivative is when you differentiate the first derivative. You differentiate once, you get the first derivative. You differentiate the answer that you have just obtained, what you get is the second derivative. If you differentiate again, what you get is the third derivative. And so on and so forth. Okay? Now that's why I said in general, if y is differentiable n times, because it has to be differentiable n times. The fact that it is differentiable 2 times doesn't mean you can differentiate one more time. For example, look at the quadratic function. You differentiate once, you get a linear function, yes? Differentiate that linear function, you get a constant, right? Differentiate the constant, you get 0. How do you draw a graph of 0? 0, like y is equal to 0. That's just the x-axis, right? So you want to find the derivative of the x-axis. There's no derivative, it's 0. Okay? So that's why I said it is differentiable n times. So note the following symbols. dy dx is the first symbol that you know, the Leibniz notation. For second derivative, the square is on y and d here, and on x here. It's actually the d dx of dy dx. I'm sure you are familiar with this one. So we pronounce it as d2y dx squared, not the square y. d2y dx squared. So similarly, this will be dny dx to power n. Does that make sense? So in terms of the function notation, you just put 2 prime, like that. Okay? You put 2 up to 3, I think. Then from 4, you start putting it in the bracket. Because instead of using IV, okay, so you use normal number. 4 in the bracket, 5 in the bracket, 6 in the bracket, and so on. But for the first, second, third, and the derivative, you just use the prime, like that, without any bracket. Understand? So let's just take this. We're going to have practice tomorrow, briefly online. But I want to introduce it in class so we don't have to waste too much time teaching. This especially, you remember last week I gave Lillian some questions. So this is the aspect. Because I said, oh, we're going to do it next Friday. Luckily, we were able to catch up with that time. Let me take 1 or 2 questions from here. Let's take, find the second derivative of, give me the first one. Find f1 prime x for, yes?
3x squared.
For 3x squared, or f of x equals 3x squared, yes?
Yeah, minus 6x.
Minus?
6x. Plus 2.
Plus 2. So, what you do, you start from the first one. The first derivative, clearly, is what? Together? 6x minus 6. And second derivative means differentiate this result, not here. What's that? 6. And your third derivative will be what, if necessary? 0. So you can't even go beyond 3 times. Okay? Let's take more. Give me this. This is mathematical induction. Yeah. We have time for induction. Yeah, I can quickly do it. I hope it's not part of. Yeah, we can quickly do it. Give me that question, quickly.
Suppose
y equals to
capital A.
What? Capital A exponential
e to the power of bx.
E to the power of bx, yes.
Where a and b are constants.
Okay, so I just say a, b belongs to r, yes.
Proof by mathematical induction that dny divided by dx
dmy divided by dxn, yes.
equals to b to the power of ny.
B to the power of
n
n
and then times
and y, like this.
Yeah.
Okay. This is proof by induction. I just gave that by induction part. Usually proofs like this is by induction. So, you want to prove that the nth derivative will always be this. How do you prove by induction? You test one of when Pn is true, right? Pn is true means when you differentiate P1 is true means when you do the first derivative. Remember, Pn is this. Let's Pn be the proposition that the ny, the x to power n must be bn to power y, bny. This is the statement I want to prove. Okay? My P1 will be that the first derivative must give me this. So for n is equal to 1, okay? For n is equal to 1, I will get dy dx, right? That's when n is equal to 1. Dy dx from here will be a times bx. No, let's follow the normal. This is a constant. You write first. You copy and paste the exponential. Then you multiply by the derivative. Do you agree? And that is going to be b times a exponential bx. Is that not? Which is equal to what? by. And that is b raised to power 1y. So which means this statement is actually true when n is equal to 1. Are you getting my point? You don't have to do b2, but I'm just going to do it. For n equals to 2, that means we are talking about the second derivative now. Second derivative means go back and differentiate the first derivative. So I will start from here, not here. Okay, my second derivative, the 2y dx squared, together now, from here. B, talk to me please, quickly, fast. A, exponential, bx times b. So I can write that as b squared a exponential bx, which is equal to b squared y, right? I should say here that this implies that P1 is true. Okay? This also now implies that what? P2 is true. Okay? Then we always have an inductive hypothesis. Okay? What do we say? Suppose that what? Pk is true. What does that mean? That is, yes? Speak louder, please. D dky, dx to power k equals to b to power ky. This is a supposition. Okay? Then we prove for n is equal to k plus 1. Okay? Suppose this is true, then for n equals k plus 1, that is, we want to prove d. Then for n is equal to k plus 1, dk plus 1y dx to power k plus 1. This is what we want to prove. You want to prove that this will be b raised to power k plus 1y, right? So this simply means d dx of what? D dx of? Can you speak louder? Who is speaking? I can't hear you. Yes? dky dx from what I said here. You have to differentiate something to be able to get the k plus 1 derivative. Then you must have differentiated the kth derivative. Are you with me? So this kth derivative is actually your proposition. So which means we are talking about d dx of b raised to power ky, right? Which means d dx of b raised to power k times, what is your y? A exponential bx. So try to differentiate this. B raised to power k, a is a constant. So you copy this exponential bx times what? Times b. Clearly that is what? B to the power of k plus 1 times a exponential bx. So this is simply what? B to the power of k plus 1 y. And because we have been able to show that also, so since it is also true for n is equal to k plus 1, then it is true for all values of n. And that ends your proof. Understand?
Yeah.
Okay? That is where we will stop for today. I will write, so the conclusion will be, since b k plus 1 is true, is also true, then Pn is true for all n in natural number, right? That's the conclusion. So this is enough, or you can say, therefore, this is true for all n. If you don't want to say that Pn is true, you can say from these things, okay? Or you can say since pk plus 1 is also true, then give me the statement. dny, yes, dxn is equal to bn to power y for all n belonging to n, or z plus. Understand? Thank you very much.